Thank you. Thank you. Yes, I try to record a couple classes and then post the one with the least amount of technical difficulties, it turns out. And so here, we got our equation for momentum and kinetic energy. If we solve the momentum equation for either mass or velocity, we can then plug it in to the kinetic energy equation, and you'll see the result there. So what do we want to do first? We'll do both, but mass or velocity? Mass. And so if I solve the momentum equation for mass, well, that would be momentum divided by velocity. And I can take that equation and plug it into the kinetic energy equation and see what we get. We'd get kinetic energy equals 1/2 P over V times V squared. And what do you notice happens? One set of V's cancels. And so we end up with KE equals either 1/2 PV, or you can say PV over 2. And so when would this be helpful? Well, maybe I have two objects. I know something about their momentum and speed, and you can use this to figure out what's true about their kinetic energy. So if they have the same speed, maybe different masses, the momentum and kinetic energy are directly proportional. What if we solve it the other way? What if we solve for V, it'd be momentum over mass. And I can plug this in to the V. And so we'd get KE equals 1/2 M times P over M squared. Now be careful here, who gets squared? Both. And so we would have KE equals 1/2 M times P momentum squared over mass squared. And we can reduce the mass by one set. And we'd end up with momentum squared over 2M. Or you can say 1/2 momentum squared over M, right? I just combined the two denominators. Good deal? And so every once in a while, it's good to do this. AP sometimes will have you derive for a certain equation in terms of, and whatever they list out is what should be in your answer. So this one's in terms of mass and momentum. The previous purple was in terms of momentum and velocity. Good deal? Okay, so that's the only little notes there. Page 6, it looks like we did that already. And so just a reminder, 2D conservation. We're actually going to start with one of those free response questions that has 2D conservation. AP College Board says qualitative and semi-quantitative. So qualitative is the vector stuff that we've already done, right? If one part goes up, the other part has to go down. Semi-quantitative, I guess that's what we did. We didn't have heavy, I don't know really how to define semi-quantitative. Numbers, but not hard numbers? I don't know. And so just be ready for it. This one was a special case. Do you think every 2D collision is going to have equal mass? No. Do you think every 2D collision is going to be both at 45 degrees so that it's 90 total separation? No. Okay. So that's why I did what appears to be complicated setup, but your horizontal momentum, your vertical momentum is always conserved in a collision. Again, I said always, I hate that. Most of the time it's conserved as long as there's no net external forces. Okay. Do an impulse on the system. It's that asterisk to our conservation. And so I believe in the AP practice section, if you're using OneNote, I try to title like sections, mainly for myself. I believe page 21, yes, is a 2D free response. So let's start with that one so we get some 2D practice. And then maybe we have some independent practice time with some of the other free response, okay? And so today my goal is to, do some of those midsection free response practice. Next class, we'll get into some of the NIMSY. Or maybe we do a little of each day, right? NIMSY, free response practice. Page 21, find this piece of paper. Hopefully you numbered your pages. You were maybe had to number your own pages because you can't trust. It's one of the things I forget to do before I make copies. I'm sorry. You're lucky if you get copies, right? Okay, so here it's going to look a little similar. We've got two objects in the beginning, but not equal mass. And notice they are not going to have a head-on collision. So I think last time I talked about a glancing collision. And so in billiards, sometimes it's a strategic move not to hit the target ball in the center. Sometimes if you want the target ball to go right, you got to hit it on the left side, right? If you've been watching curling, they do that all the time. Okay. And so these glancing type of collisions, not head-on. And it results, you can see in the after collision picture, we got a 37-degree angle. Okay. Two objects, 1 kilogram and 4 kilograms, are free to slide on a horizontal, thank you, no ramps, frictionless, no net external forces, surface. The objects collide and the magnitudes and directions of the velocities of the two objects before and after are shown. And they go on and tell you, and I think this is on the front side of the formula chart or the other side. If you didn't have a scientific or graphing calculator, what is sine, cosine, and tan 37, in case you need it? Calculate the x and y components of the momentum px and py of the momenta, plural of momentum, for the two objects before and after, and write your results in the following table. And so this table, 1 kilogram is the first two columns, 4 kilograms is the second two. The first row is before, the bottom row is after, and then the only other difference in the columns is that x and y for each mass. So make sure you get things in the right location, okay? And so going up above, what about before? Let's look at ball 1 kilogram. Before the collision, in the horizontal, how would we find its momentum? M times the initial horizontal velocity. Well, thankfully for us today, it starts out all in the horizontal. And so it would be 1 kilogram times, let's say, a positive 16. Did they define the positive direction? No, so we'll just go with standard sign convention. Up and right will be our positive. That's usually the norm. Unless you have a good reason to change, that's usually the norm. And so 1 times 16, we're going to get 16 in our first square on the table. What about the vertical momentum for object 1? 0. If you only move in the horizontal, there's nothing vertical about it. Then let's take a look at the second object before the collision. I'm going to do all the before collision first. And so the first, M2, the 4 kilogram, well, in the picture it says it starts at rest. So does it have any momentum? No. So 0, 0. Now, it's not an additional problem here, but the sum of all the momentums, okay, x, the sum in the y before the collision, well, the sum of horizontal plus horizontal, 16 plus 0. Vertical would be 0 plus 0. Good deal? Okay. After the collision, ball 1, what does it do? Well, if we go back up to the picture, there's no more horizontal. So the horizontal square would get 0. Does it mean that the next one is 16? Conservation of momentum isn't per object, it's per dimension. And so no, it's not 16. If we go to the picture, the momentum final for ball 1 in the vertical would be 1 times what? Negative 12 if we go with sign convention, right? Correct? And so we would get a negative 12. Now don't start telling yourself 16 doesn't equal negative 12. That's a correct statement. It shouldn't, and it doesn't. What about the 4 ball? They give us the speed of 5, and notice I'm getting technical here. That's a speed. Velocity has direction, speed does not. And so the hypotenuse, hopefully you can kind of visualize a right triangle. And so the speed is 5. How are we going to find the horizontal and vertical components of that speed? Sine and cosine. And so Vx for object 2. And then we'll have, I know it's not a complete triangle. I'm trying to, adjust for the room. And then Vy for object 2. So for the x one, you can see they show the 37 degrees is adjacent to the x component, traditional, if you will. And so we'll use cosine 37 to find Vx for the second object, divided by the hypotenuse of 5. And so grab a calculator, or maybe you look down below, cosine 37, a convenient 0.8. And so 0.8 times 5, 4 meters per second. By the way, 37, AP usually uses 37 or 53 because it gives some nice function values. And then while we're here, let's do the vertical. And so vertical component, true story. Could we do Pythagorean theorem or tan if we so chose? Yeah, now the norm, textbook norm, is to go ahead and use the given speed and use sine, okay? And so sine 37 would be that y component of the second ball divided by the hypotenuse, which is 5. And down below, again, if you don't have that calculator, sine 37 is 0.6 times 5 would come out 3. These are the velocities. These are not the momentums. To get each of the momentums, we got to multiply them by mass. And let's consider direction. Right and up, both of these components would be positive. And so the second ball has positive momentums. And so 4 times 4 is 16. And that was the horizontal, I believe, right? And then the 4 mass times 3 vertical component is 12. And so if we notice the sum of the momentum in the x direction here, 0 plus 16, the sum of the y, negative 12 plus 12. And if you didn't consider that, you're about to be forced to. So we got the data table filled out. B, show using the data table that you listed above that linear momentum is conserved. They're looking for 2 separate conservation statements. And so the net initial horizontal has to equal the net final horizontal. So looking at the first column and first row, 16 plus 0 equals second row, still first and third column, 0 plus 16. Check, it's conserved. Same thing with the vertical. So it equals the final momentum in the vertical. So this is the first row, second and fourth column, 0 plus 0, equals, after the collision, negative 12 plus 12, which equals 0. So check. Good deal there. Okay, what about calculating the kinetic energy of the 2 object system before and after the collision? So we know mass and velocity. Wait, does kinetic energy need velocity or speed? Really speed, okay? Does energy care if you have 2 dimensions? Are we going to have a horizontal kinetic energy statement and a vertical kinetic energy statement? No. So a little reminder, it's scalar. So there's only one conservation. So, well, oh, hold on. We don't know if it's conserved. They're telling us before and after. We'll see if it's conserved, right? We don't know if it's conserved, but the sum of the initial kinetic energy will be the kinetic energy of the first ball. The second ball had none, so if you want to just show that concept, plus 0. Kinetic energy of the first ball, 1/2 m1 times its initial speed squared. And we know both of those numbers. The first ball was our 1 kilogram, I believe, right? And it was traveling at a speed of 16. So 1 times 16 squared and half that. So let me know what you get when you square 16 and take half. And by the way, so this is an old APB question where they did more calculations than you'll do in May. Here, they'll just kind of keep it in variable form, which is why I try to keep my variables until the very end. I hear 128 in the SI unit. Joules, energy. Okay, so that's before. Let's do the same thing for after. And so final, they both have kinetic energy after the collision. And so 1/2 m1 v final squared plus 1/2 m2 v final squared. And again, those are speeds. It doesn't matter about direction for kinetic energy. And so 1/2 of 1, how fast, what's the speed of our 1 kilogram ball after the collision? Just really 12. I mean, if you put a negative in, it's going to square away. But at the end of the day, it's just a speed equation, scalar. Plus 1/2 of 4 kilograms. What's the speed, 3, 4, or 5, of the 4 kilogram object? Is it 3? Is it 4? Is it 5? Is it 7? What do we do here? It's 5. It's the speed, the actual speed of the object without any direction consideration is 5. So I'm just going to highlight that one because that's probably a point where some students are going to either not know what to put in or they might put in the wrong thing. So that's the only reason for the highlight. And so 12 squared, half that, 72. And then we got 5 squared, 25 times 4, half that. And what is our final kinetic energy after the collision? 122. Wait a second. Wait, let me make sure that's not the next question. Oh, it is. Is kinetic energy conserved in this collision? No. What kind of collision would we classify this? They bounce off each other. They don't stick together. Momentum is conserved, but kinetic energy is not. Partially inelastic. Now, I will say at the end of the day, AP may not use the word partially or perfectly, okay? That's just how we distinguish between them. And a lot of textbooks do that. But at the end of the day, it's just inelastic, okay? Inelastic. Question. Where do the other 6 joules go? Yeah, where do the other 6 joules go? Let's answer that as a class. It's heat loss typically, okay? And so officially you can say heat loss, or AP may say, oh, it's internal to the system. So it's an internal energy loss. Because AP1 doesn't do thermal dynamics, so they may or may not use the word heat. But internal to the system, when those balls hit, they're going to touch, okay? Now, it doesn't say what they're made of, and so that touching is probably going to be some frictional losses, okay? Questions on a 2D conservation? It's really nothing new. It's just an extra statement in momentum, right? Okay, how about let's do, let me take a look. Hold on. We did 15. We did 16. 17 is variables. Ooh, I like the justify. Oh, no, let's do this one. Let's do this one. This one has a uniqueness about it. So page 18 and 19 we'll do together. Say again. I'm sorry, I just don't understand what you're saying. You said that the 16, well, these two 18, these pages are the actual full 16. We just did 21. Oh, the packet did not write this. Yeah, OneNote puts these page numbers for me, and I don't always remember to edit or write page numbers before I make the paper copies. So day one, that's what I said, y'all make your own page numbers. So top page is page one and then subsequent. Anyway, I'll try to remember for the next packet. I try, y'all. Okay, so here we have two cards. By the way, this was a AP Physics 1 question a few years ago. So this is what you'll see in May. This is what we're not, put the calculator away. We probably won't need it. Card A on the left has a mass of 2m. It's released from rest from a height of h on a ramp that makes theta with the horizontal as shown above. So sentence 1 just described what we see on the left. Cart B on the right has a mass m. It's released from rest from a height of 2h on a ramp that makes angle 2 theta with the horizontal. The carts roll towards each other and have a head-on collision on the horizontal portion of the ramp and stick together. Ooh, stick together. The masses of the cart's wheels are negligible. And you're like, why would they tell us that? After spring break, when we look at rotation, it matters about the wheels, okay? Because they take some energy to rotate. Here we neglect it. And so there's no rotational energy. I'm just going to tell you that's why. We haven't learned it yet. So after spring break. And there are, as are any frictional or drag forces. So no friction, no drag due to air. And so are we going to have any net external forces acting on the system? Actually, normal force could be considered an external force. Is it going to do any changes to the energy or momentum? No. Okay. And so, oops, timeout. Hold on. Let me get back. And so in terms of external forces on the system, there's no work or changes in momentum. Okay. State whether the carts remain at rest, move to the left, or move to the right after the collision. And notice we have a checkbox. Maybe there's 1 point if AP is being generous, but I'm going to tell you, usually on a free response question, no points are tied to checking the box. So what happens if you check it wrong? Doesn't matter. No. So what I've heard in the past, now I've never graded this type of question, but what I've heard from other graders is if you check the wrong box, they don't even read what you write. It's not a paragraph response like we saw last time. Now, note to self, paragraph response, they will read it no matter what you check, no matter what decision you make. They will read it, okay? But for these short justifications that are maybe only 2 or 3 points, if you don't check the correct box, they don't read it. Don't check all 3. Here's your test taking strategy, okay? I save the checkbox for last. I'm going to go through the physics first to get my answer. Now, at the end of that physics, if I'm still not sure which one to check, don't check any. So your little test taking tip, if you're not 80, whatever, 70, 90% confident on which one to check, don't check it. And then they will read it. is what I've heard, okay? So forget the checkbox. What should we solve for? Before we write a sentence to explain, by the way, they're not expecting a paragraph here, okay? You can do the physics and then maybe end with 1 or 2 sentences to help connect it, right? So, someone last time mentioned CER. So before we make the claim, let's look at the evidence and reasoning first. And so, what would we be solving for to answer this question? What would our unknown be? Which V? Which final? Of both after the collision. And so we want the final velocity of both cars, the system, after the collision. And you may be wondering, well, why doesn't F give it away? It's after the collision. Well, each object starts at the top of its respective ramp. If you call that initial, one could call final, your first final, your intermediate final, however you label it, before the collision at the bottom of the ramp. And yes, we're going to, okay? And so that's why I'm being very specific about what we're solving for. So that's what we need to know after the collision in order to answer that question. Well, before the collision, what happens? Each cart has a height change. Height change, what should we do? Energy. And so step 1, let's do energy. Now they said that all the surfaces were frictionless, right? And so we have conservation of mechanical energy. This is including the earth in our system, right? So we have the carts and earth as our defined system. It's the easiest thing, most common thing to do. And so if you just look at one cart, it begins with what kind of mechanical energy? Potential, gravitation, initial at the top. And by the time it gets to the bottom of the ramp, but before the collision, I'm going to add that in. And these aren't necessarily required for the grader, but it's kind of being nice to your own self so you can keep it straight, okay? So when it makes it to the bottom of the ramp, but before the collision, all that potential energy is converted into kinetic. So at the bottom, but again, before the collision. And now we can plug in the equations for each. Potential energy is mgh. Kinetic energy is 1/2 mv squared. Now this is for each cart. Okay, this is a generic statement that you can apply to each cart. So if I'm looking at one cart at a time, what do you notice? MA on one side, MA on the other, MB on one side, MB on the other. Masses can cancel. If I just look at one car at a time, this equation is going to apply to both. And so it's not dependent on the mass, right? At least for the going down the ramp. And so we would get an equation. And by the way, if we're doing this to get us to conservation of momentum and the collision, we were probably wanting the speed, the velocity, right? And so V would equal square root of 2gh. And this is initial for the collision. Notice I just switched it, right? So this is initial before the collision. Because I need to now take this intermediate velocity and do what? We really want the final velocity after the collision. So collision, collision, what's your strategy? Momentum. And so now let's do conservation of momentum. Since we said there's no net external forces that are going to do impulse on the system. And so the net initial momentum equals the net final momentum. We're not going back to the top of the ramp. This is all now at the horizontal part in the middle. before the collision, who has momentum? Both. So P1 initial plus P2 initial. After the collision, who has momentum? Both system, because what do they do after the collision, they said? They stick together. So I can say final of my system, and that's just a note to self that they're going to stick together. They have a shared velocity, right? And so we can come in and say, well, M1 V initial plus M2 times its initial. Wait a second. It's a head-on collision. What little change can I make it? Either now or later, I got to make it. Momentum's a vector. So who's going to be negative? Yeah, part B or 2, we can make that a negative, and I'll change color just for emphasis. And so a negative velocity, you could say you're subtracting the momentums, right? Yeah. We'll get to that point. But at some point, you got to recognize that. So energy was solving for a speed, but here with momentum, you got to consider direction. Equals my system mass, M1 plus M2. And then that final velocity after the collision is what we're solving for. Everybody good? Let's put it all together. So we know the equation for energy. Before I plug them in, let's figure out what they are. So VIA would be the square root of 2G. That's going to be part of the equation. But what height specifically does cart A travel as it goes down the ramp? Capital H. I switched to capital because that's what they gave me, right? What about VI of B? It'd be the square root of 2G times 2H. And we can actually take that one a little further. 2 times 2. Square root of 4. I can pull the 2 out. Okay, or keep it in, just make it square root 4GH. This isn't a final answer, okay? And so now that I have those, and if I didn't recognize the negative, I'd probably want to right about now, okay? And so I just don't want you to think I'm going to double negative. What do I mean, what? In the problem, cart B traveled a vertical height of 2H. Yeah. Okay. Say what? Never mind. Okay. And so now we're going to use those velocities to plug into our momentum equation. And now we do have to take into account mass because the mass is not going to cancel out, at least completely like it did in energy. M1, we were told, is 2m times its initial velocity, which we said is positive, times the square root of 2gh plus m2, minus, right? We can pull the minus. We're going to subtract that. M2 is just m, and its initial speed, since we've already taken into account the sign, is times 2 times square root of GH. Or if you wanted that square root of 4, GH is fine. Equals the system mass, which is 3m. And there's that final velocity after the collision that we're trying to solve for. Just gonna keep that one highlighted. Woof, all of this just to check a box, right? Yeah. And so now let's simplify. What do you notice? The m variable cancels, but the factors remain. And then what are we going to do to solve and simplify? Let's see. Somehow we got to combine like terms here. We got the 2. Would it have been easier to Oh, okay, okay, okay. Put the numbers together, put the variables together? Okay, so 2 times the square root of 2 times the square root of GH. So that's the variable that we're going to do combining, minus 2 times the square root of GH. So there's our combined like terms. And then all over 3, I did a double here. And so if we combine that top part, 2 times the square root of 2 minus 2 would come out to be. And if you have a calculator, if you want to simplify, huh? I'm doing to combine like terms. What number times square root of GH? 2 times the square root of 2. 0.8. We get a positive number. Really, that's all we care about right now, right? We're going to get a positive number. And so I hear 0.8. Now, yeah, you can simplify the 0.8 and divide it by 3. Or to check a box to know if it goes right or left or stops. Does it stop? We didn't get 0. We got a positive answer, which means it's going to move to the right. Whatever we said was positive, and we went with standard sign convention, so to the right. If I remember correctly, there wasn't a point for the checkbox. There was a point for using conservation of momentum. I'm sorry, energy. There was a point for using conservation of momentum. There was a point for designating direction. So that one was one that if you think too fast, you're so used to energy being scalar, you forget that momentum's a vector. So if you miss that red negative sign, okay, you wouldn't get that third point. And then for getting, combining like terms and getting a positive answer type would be maybe that fourth point, okay?
How much time should we actually be spending on this problem?
So this one, I think, it doesn't say, and I'm gonna add, yeah. I can't remember if this was a 12-pointer or a 7-pointer. If you remind me later, I'll look it up. Let's keep going. Next page, continuation, but a little bit different. Same picture. It says, consider the time interval from when the 2 cards are released from rest. Remember that? They didn't remind us, but it was released from rest until just after they collide. By the way, if you answer these questions from when they're released till they go to the bottom of the ramp before the collision, you'll get the wrong answers, okay? And so notice they're very nitpicky where your initial and final points are. For the system, this gets back into those system designations. So part 1, if our system is 2 carts in the earth, indicate whether the total mechanical energy increases, decreases, or remains the same. Justify, and we'll come back. But part 2, what if your system is just the 2 carts? Same question. And so you remember last time with energy, you got to figure out how to approach this 2 carts in earth or 2 carts only. And so total mechanical energy. So this part is just really review. Total mechanical energy, or change in mechanical energy, was our work done by non-conservative forces. When you include the earth, are there any other non-conservative forces doing work? No, it's all frictionless. We said normal force is perpendicular, so it's not going to do any work. Remember, for work, it's got to be parallel. And so we don't have any non-conservative works. And so again, work done by normal would be 0. Work done by friction is 0. Gravity's included since the Earth is included. What about the force the two carts exert on each other? The applied force at the hit. Say again. Well, there's going to be some thermal, no, did they specify? Hold on. Neglect any frictional forces. So even they're going to hit, there's an applied force, but it's internal to the system, right? And so we're not going to include that one. And so what's going to be true? It's going to remain the same. The energy we begin with at the very, very top, all the potential energy for the system initially is going to all be converted to kinetic energy of the system after the collision.
Well, didn't you say that able to prove the previous one, we had to make ample energy at the beginning?
Say it one more time. This was all before the collision. We're trying to get to after the collision. And actually, it's just dawning on me. We talked about the collision. What kind of collision is it? It's completely or perfectly inelastic. And here's actually where we're going to get our answer. Is kinetic energy conserved before and after the collision? In a perfectly inelastic collision? Right, because they stick together. It's completely perfectly synonymous. Oh, there we go. Yeah, they stick together, so it's a completely inelastic collision. Is kinetic energy conserved? No, and so maybe here, this kinetic energy at the bottom of the ramp, but it doesn't equal the kinetic energy of the system after the collision. So this one would be before the collision. And so we kind of have that intermediary spot. And so your mechanical energy due to the type of collision is increase, decrease, stay the same. It'll decrease. Your final kinetic energy of the system after the collision, again, this is for you, is going to be less than the kinetic energy. So yeah, the heat between, due to the nature of the collision, it's not, we don't have a label for it, it's that internal energy. And this is before the collision. Okay. Perfectly inelastic, kinetic energy before and after, not conserved. This makes sense? Okay. What if it's just the two carts? What if it's just the two carts? So then mechanical energy initial is equal to what? Gravity is going to be outside, but it's just the kinetic energies of the systems, right? And in the beginning, what is that kinetic energy? Nothing. They're released from rest, right? Released from rest. And so initially, do we have any mechanical energy? No. And then we don't even need to consider the intermediate. At the very end, after the collision, do the carts have kinetic energy? Yes. So they have some kinetic energy after the collision. And yeah, there's been heat loss, or I guess, yeah, for internal energy losses with the type of collision, but it's more than zero, right? And so what are we going to check? It's going to increase. It goes from nothing to something. Yeah, it decreases during the collision, but they started us at the very, very top. Remember I said at the very, very beginning, notice that they started at the top of the ramp and we end after they collide. Okay, So there wasn't really momentum on that one, but could they ask if momentum increases, decreases, or stays the same? Depends on what situations you would look at, right? So with a collision piece, it would remain the same, but from very beginning to very end, momentum for both systems would increase, right? They went from no momentum in the very, very beginning to having momentum at the very, very end. Okay. So there's that one. How about, I know it's not the easiest. Let me make sure we've done the others. Actually, let's save the variable. We'll save 17. Let's go straight for the NIMSY free response, because I know F1 should be a moderate challenge. It's not the hardest, it's not the easiest. How about we end, oh gosh, we got a lot of time. We'll pause. I don't know, maybe we come back together. I'm gonna give you 15 minutes to do page 27, and that's it. F1 in your NIMSY packet. So take about 15 minutes, small group this one, and then we'll go over it and do something else. A crossbow is a device that fires a dart at a very high speed. So this is kind of like the bullet gonna get fired into. This is a ballistics pendulum, okay? Ballistic pendulum that we saw last week sometime, right? It says a student wishes to determine, here's the unknown, that the dart exits, the crossbow wishes to determine that the dart is there a misprint in that sentence? Yeah, that's usually not, it's usually not a yes or no determination. So let's pause, let's come back to that second question. I feel like there's a missing variable. What are they really trying to determine? Maybe a speed. Maybe it's to determine the speed that the dart exits. So I'm going to put that here and I'll cross it out if we determine otherwise. The student cannot simply divide the distance by time. So I think speed's a good assumption because no equipment that can accurately measure time is available. This happens quick, right? The student is only provided with a wooden block. So the only equipment, wooden block, some string, a meter stick, a protractor, and an electronic scale. So no timers whatsoever. You cannot measure time. You can calculate time, but you can't measure time. Good? So on these questions, make sure you don't start talking about using a timer. There's not one in the room. The student determines that the best course of action is to hang the wooden block from the ceiling by the string and fire the crossbow dart horizontally. Why do it at an angle, right? Into the block so that the dart sticks. Hold on. Sticks to the block and the block swings upward. So this is like that simulation, or I showed you the real life demo, yes? The ballistics pendulum. And so that's what's going on here. In the space below, explain what measurements the student must make in order to calculate the speed of the dart. So maybe we need to know the setup of the calculations so we know what to measure. So typically your electric scales, it's not a force scale, it's going to give you mass. They usually say spring scale or force scale to measure force. Those do exist. Okay, draw a diagram of the setup that shows a labeled geometric quantity that is being measured. So if we're doing this like the ballistics pendulum, y'all want one string or two strings? Two prevents rotation. We haven't studied rotation yet, so I think two is our best bet. We'll only need to focus on one. And so this is the block, the wooden block. Okay, our dart maybe is going to get fired from the left-hand side. And it's going to go into the wood. We line it up horizontally. And then sometime in the future, maybe we have this setup, right? And so each of the strings makes an angle with its previous vertical position. Now I know that somehow the block shrunk. Maybe if this was the AP exam, you pay close attention to that. Okay. They don't grade with a ruler typically. But what are we going to measure? And it says label the geometric quantity that's being measured. Okay, so we got an angle. And so how are we going to measure the angle? All right, with a protractor. What else might we measure? What distance? The block. And so from that initial height to the final height, that change in height. And so if I talk about measuring a change in height, I need to label it on my diagram. Change in height is going to be measured with meter stick. And I don't know if you remember when we did this calculation last week, the simulation, you really don't need to measure both. You just need one. What else could the meter stick measure? The distance the arrow traveled wouldn't help us because we can't measure time to get the velocity. What did you say, Sharon? Length of the string. So I got to label it on the diagram. So L can be measured with the meter stick. Anything else to be measured that might help us find the velocity? Mass. And so maybe MW and MD I label. So MD and MW would be measured with the scale, the electronic scale. Good deal. And we don't have to really explain how we're going to use these measurements in part A. That's actually part B. And so I think that's going to take a little bit more than two. I don't know. Let's see if we can get it started. Do y'all remember the two-step process to finding the speed? What two steps are we going to have to use for how these measurements can be used to determine the initial speed of the dart? There's a collision. So for the collision part, what's your strategy? Big idea. What's the physics? You could do impulse, Newton's third law. And if you know both masses and you're going to calculate the speed, really this is easier if you do conservation of momentum. In my opinion, collisions, plan A, conservation of momentum. But we don't have an angled collision. The angle comes from the swing. What big idea, physics principle, are we going to use for the swing portion of the problem? Not centripetal if you measure height, energy. So that conservation of mechanical, and one note, quit writing. I guess perfect timing, end of class. How about that? Thank OneNote.